been occurring for finalizing the room. I don't want to start as long as the room is not closed. I hope you enjoyed the keynote lecture and had some chance to take a coffee in the short break. No? But you're still smiling. That is the most important, with or without coffee. So, yeah. So, with respect to time, my time here for session introduction is more or less over. So I think I will start now. Yeah, ladies and gentlemen, my name is Jürgen Stamm. I'm happy to have the chance here to moderate this groundwater session. It's groundwater management. That means we talk about quantitatively managing the groundwater resource and aquifer. So we don't talk about, it means quality aspects, which has to do with groundwater contamination and so on. But even the management of the water resource, the invisible water resource and the aquifer is very important. Sometimes forgotten from the public because you don't see it, and it's so we said here managing the invisible resource groundwater, but not less important than river and sea and reservoirs, of course. And changes in the groundwater, since they are not immediately visible, people they are not aware of this, and then the impact is much longer. Groundwater slowlier, impact much longer in both directions, whether we have high or low groundwater tables, and it's very important that we have a good integrated groundwater management. So I'm happy that we have 5 presenters here, and all the presenters are here mainly from India, from Bangladesh, and from Australia. And we have 4 cases which will look at India, and 1 case which will look at along the Mekong River. We are looking forward to hear your presentations. Please, on all presenters, take care for the time. I want to be very punctual. Now it's 1 minute later than the official start, and I ask the first presenter, Mr. Shubham Tiwari, to come to the stage here and give us your presentation about aquifer storage and recovery as a solution to ensure water availability in saline groundwater regions. Mr. Tiwari, please.
A very good morning, everyone. A very good morning, everyone. I am Shubham Tiwari from IIT Roorkee. Today I am presenting on aquifer storage and recovery as a solution to ensure water availability in saline groundwater region. So first I would like to talk about the problem of groundwater salinity. So groundwater salinity is 24 million square kilometer area worldwide, which is 16% of the total land area of our planet is affected by the groundwater salinity. Mostly, as you can see in this figure, mostly West and Central Asia basins are highly affected by the groundwater salinity. If we talk in the case of Indian scenario, in India, 2 lakh square kilometer area is affected by groundwater salinity. And India is an agricultural economy, and we are using 85% of our drinking water supplies and 60% of our irrigation supplies by using the groundwater. So it is a very big problem in case of our country. And for example, there is a district called Mewat district, which is having 78% of aquifers as a saline groundwater. So we are having a big problem. So we got a project from Government of India to find a solution for this problem to make freshwater availability in this region. So we explore different managed aquifer recharge methods to find out that how we can ensure the freshwater availability in this region. So we got two different manage aquifer recharge methods which are known as ASR and ASTR, which can solve these problems. Then we explored these solutions. So what is ASR, aquifer storage and recovery? In ASR, we inject the fresh water which is available on the excess, like in the rainy season. We collect that water and we inject, and this injected fresh water pushes the ambient saline groundwater and makes a buffer zone, which buffer zone actually reduces the mixing rate within the aquifer, and it makes durable to store the fresh water within the ground, within the saline aquifer, and we can store it for longer durations, and we can take it out when it is required on the surface. So this is the climatic condition of my study area, which is called Mewat district, and it is showing the mean rainfall and temperature of the area. As you can see in this graph, there is a very small duration rainfall in this season. So we have planned that during the rainy season, we will collect the fresh water by different means and will inject within the aquifer. And in the next phase, we decided that this phase is will be the storage phase, where injected fresh water will be left out into the aquifer for this duration. And at this time in the recovery phase, this is the phase when temperature rises and the fresh water is required on the surface, and will take out the fresh water at the surface. And this is how we have planned our ASR cycle yearly to ensure the fresh water availability on the surface. So this is obvious that when we will inject the fresh water within the saline groundwater, we cannot recover the whole water which is injected, because there will be some losses which depends, there will be mixing and gravitational segregation. All these, due to all these losses, we can only take out a portion of water, and that portion is known as the recovery efficiency. So first question came to us that where we can establish this ASR scheme. So we have to explore the hydrogeology of that particular region where we have to establish this ASR scheme. Another comes that how to design the ASR well, and next question came that how to operate the ASR scheme and what will be the role of different fluid properties. So keeping in mind all these questions, we have tackled this problem and developed a stepwise implementation plan for our scheme for my study area. And in the planning phase, we have find out different factors that which can affect, like what should be the source to recharge, what could be the potential uses. And another is investigation phase, where we have investigated different hydrogeological properties on the field, and it helps us to decide the site selection procedure. And next phase comes as design, where how we can design the SR well in such a way that we can take out maximum amount of water which have injected. And last one is the operation phase, where we have to optimize different operational parameters such as rate of injection, extraction, what should be the storage duration, volume, etc. So for this purpose, we have planned I have planned my study in two parts. First, I have before going to the field, I have done the laboratory experiments for unconfined and confined conditions. And as you can see in this figure, we have taken a sand tank. In that sand tank, there were different monitoring layers, where we took the samples from different ports by using the syringe. And in this case, I am giving you just one example, and we have done this for whole all the factors which I have explained, and I am giving you example how we have done for one factor, such as in the shallow aquifer, we have gone for the different depth, release depth within the aquifer, and we have taken 3 different depths, and we performed the experiments and find out that what is the behavior of injected fresh water within the aquifer and how it behaves. So this is how we have taken for all the depths, we have taken the samples, and we find out, and we also with the help of this observation, we also made a model by using the mod flow and CWAT, and we have taken that, we have observed that how this stored fresh water is going to behave at different depths, as you can see at shallow depth and moderate and deeper zones. So after 1 hour, after 2 hours, 3 hours, 4 hours, within laboratory experiment, we find out the behavior, that how it is going to behave after recovery and by increasing the storage durations. And we have found out the results and the influence of different factor at different we found out the recovery efficiency for each factor. And next step comes that how to optimize the additional factor, that how we are going to operate the ASR scheme on the field. For that purpose, we have used a numerical modeling, which is done by the ModFlow software, which was linked with the CWET, and we collected the hydrogeological data from field. We did the aquifer testing and VES survey, lithological. We collected all the lithological data and made a plan, and then we took all other parameters as a constant and just variated only one by one parameter. And for each parameter, we have found out the sensitivity and optimize each operational parameter, so we can recover maximum amount of water for my study area. So these are the interface of my ModFlow model, which was linked with CWET, and we have calculated the recovery efficiency by using this for each factor. So here some of the results I am showing you. So first one is the storage volume, that we have optimized that what could be the best storage volume which we can inject in the field, and we can get the optimized result, maximum recovery efficiency, and other operational parameters such as injection recovery rates and influence of storage duration and influence of cycles. And this is how we optimized our results. So now I would like to conclude my study, and this is how actually the thing was that before going to the field, we had to know, we was willing to know that what is the behavior of stored freshwater within the saline aquifer, and how to maximize the recovery efficiency by changing different operational parameters. So I think this was we found out that aquifer properties, the operational factors, the design of well, the mixing phenomena, we have to check within the lab before going to the field. And it is possible to store freshwater within saline aquifer because due to the density difference, and the location and other operation should be recommended with the to ensure the success as per finding in the lab. So these are the references. Thank you very much.
Thank you, Mr. Tiwari, for your very interesting presentation, and for keeping time. You speak fast. I know why. Since he was so fast, I will give the auditorium the chance for one question. Do you have one short question to Mr. Tiwari? If not, I have a very short question. Did all the investigation, if you have done, did you done this for an anisotropic factor of 10?
Yes.
All?
Yes. All.
No change in the anisotropy? No. Okay, but
within the model we didn't.
Okay. We can discuss, because this, of course, has a very big impact.
Yes, I know from the literature it can influence that, but while going to the field, we have to check the anisotropy for that particular.
Okay. All other questions later. Thank you.
Thank you.
I asked, give hands to Mr. Tiwari. Okay. I asked the second speaker, Mr. Dinesh Kumar, to come to. Oh, he's running. I don't want to make too much stress, but you know.
Old age, I have to.
Okay.
So this is that. So I look at this, huh?
You look at.
Okay,
this.
yeah.
You immediately
Shall I start? Yeah.
Perfect team. I have
So
no
the
more
title of the
words.
presentation is Factors Influencing Groundwater Behavior During Monsoon in Maharashtra, India. Maharashtra is one of the western states of the country. My country is a very large state, second largest in terms of geographical area. It has a very complex aquifer system. 90% of the aquifer is basically hard rock. There is some alluvium, and there is some laterite. Yeah, I have already explained. A large proportion of the rural water supply schemes in the state are dependent on groundwater in the shallow aquifers, which receive their replenishment from the monsoon rainfall. Understanding the water level fluctuations during monsoon and what it means for the annual availability of groundwater is crucial for predicting drinking water security in the rural areas. In spite of the fact that these aquifers have very low potential, increasingly large number of schemes are being made out of based on groundwater systems, because you can have develop it locally and then supply it locally. The paper discusses the development of a complex statistical model that explains groundwater behavior in the state of Maharashtra. The model was developed and validated using district and state level time series data of rainfall, pre and post monsoon water levels, and spatial data on specific yield and recharge potential. The model considered three variables that affect the recharge from rainfall: the infiltration characteristics of the strata, the pre-monsoon depth to water levels, and specific yield of the aquifer, which have not been considered in the past investigations of groundwater behavior at such a large scale. These are district-wise rural water supply schemes in the state. You can see large, there are several thousands of schemes which are very small, catering to hamlets and villages, and 66% of them are based on wells, and 24% of them based on other sources like hand pumps, solar, dual pumps, rainwater harvesting, roof water harvesting systems, etc. And only 10% of them are based on surface reservoirs, which is very distinct from many of the developed countries, which largely depend on large reservoirs to supply drinking water to even rural areas. Rainfall in Maharashtra, you can see this, there are two distinct phenomena one can see in the state of Maharashtra. One is that large spatial differences from region to region. You find sharp differences in the rainfall. And the second most important factor when it comes to climate is the interannual variability in the rainfall conditions. If you say the rainfall in an area is 500 millimeters, it's not 500 millimeters all the years. It can vary from 1200 millimeters to something like 200 millimeters. So you really know what happens. In 1200 millimeter rainfall condition, you would expect huge amount of recharge. Well, whether that really happens, we'll see that. In a 200 millimeter rainfall condition, you may not get any recharge. All that water might end up in the soil moisture. So there are 3-4 distinct regions. One is Vidarbha, other is Marathwada, third is central Maharashtra, and the fourth is Konkan region. Konkan receives very high amount of rainfall. Marathwada is historically known for water scarcity and droughts. There was a case of tankers tankers supplying water to that a city of Marathwada region because of acute droughts. It is high rainfall region. Vidarbha gets high rainfall, but it's also a drought-prone region. Factors influencing groundwater behavior in Maharashtra. Conventional wisdom suggests that precipitation influences natural recharge to groundwater, especially in regions with shallow aquifers. Higher the precipitation, higher the quantum of recharge. A key factor in order to understand the effect of rainfall on the groundwater conditions in Maharashtra, various types of analysis were performed. In the first analysis, mean values of the spatial average rainfall of different districts were compared against the mean value of spatial average of depth to groundwater level in each district. So these water levels are monitored by the Central Groundwater Board. It's a premier agency, technical agency in our country. And there are large number of observation wells in the country which are being monitored 4 times a year. These are some of the analysis. One shows the first chart shows the district level average rainfall and the district level depth to groundwater, mean depth to groundwater levels. And the second one shows the variation between rainfall and the depth to water level. The rainfall increases, the depth to water level reduces. But then the variation is not very linear, like what Aditi was mentioning during her presentation. It's not that you have very high rainfall, you get very high recharge. No, primarily because this is a hard rock aquifer. Spatial average rainfall versus average depth to groundwater levels for the entire state in different years. Again, you can see some kind of relationship emerging when you deal with the entire state, because then when you're dealing with the whole state, you're dealing with the different types of aquifers, in spite of the fact that 90% of the aquifer is hard rock. Impact of rainfall on groundwater fluctuations, example from one division in the state. You can see how the water level fluctuation differs between years. You have a drought here, the water level fluctuation is very low, and in a wet year, the water level fluctuation becomes very high. Is rainfall only factor explaining groundwater behavior in Maharashtra? You can see the geological map of Maharashtra. The green one is basalt, it's hard rock. The yellow one is alluvium, and there are crystalline formations on the eastern side of the state. Surely it is important, rainfall is important, but not the only factor. Otherwise, the relationship, that's R square value, should have been much stronger than what we have seen. As around 90% of the state is underlined by shallow hard rock aquifers with very limited storage potential, it is quite unlikely that the recharge would increase linearly with the rainfall. Aquifer storage space could be an important determinant which is influenced by the pre-monsoon depth to water level, a factor which has never been investigated even by the Central Groundwater Board. What explains annual water level fluctuations in wells within the same geological setting? So what we did is, the state has different geological formations. We picked up a couple of districts within the state where there is no variation in the geology. So for instance, Ahmednagar district, we found the relationship is water level fluctuation is a function of the rainfall, of course, and pre-monsoon depth to water levels when we ran the regression. And similar kind of a variation was relationship emerged when we did this analysis for another district, which is Aurangabad. Now, this is a situation when you are dealing with the same kind of aquifer. What explains the groundwater behavior across regions in Maharashtra when we are encountering several different formations? The multivariate analysis showed influence of the following along with the rainfall. Of course, rainfall is an important factor. The pre-monsoon depth to water level, which we have already seen, specific yield of the aquifer, the geology, and the recharge coefficient is another important factor which has not been considered by even Central Groundwater Board when they are doing the resource assessment. It is not just the rainfall, but also the recharge coefficient. What influences the recharge coefficient is basically the soil characteristics, the surface formation characteristics, the specific yield of the aquifer. Many times we say that the water level has really come up well after the monsoon, but we often forget the fact, the importance of specific yield of the aquifer. In many hard rock formations, the specific yield is so low, like 0.01 to 0.02 in that range. Whereas when you're dealing with alluvial aquifers, the specific yield is in the range of 0.1 to 0.3. So in a hard rock aquifer, even with a very limited recharge, the water level fluctuation that you are getting is very high, which makes you believe that huge amount of recharge has actually happened. But then what happens is, after the monsoon, when the pumping starts for irrigation, the water level drops drastically, and when summer comes, there is no water in the well. So these 4 important factors need to be considered when we explain the groundwater behavior across geological settings. That's all.
Perfect.
Questions?
And perfect in time. Yeah, now we have questions. Time for questions.
I finished before time.
Yeah, I know. You did it perfect.
Yes.
Yeah, the auditorium. I look in the auditorium. Do you have questions? Yeah, there's a first.
Can you take some water?
Of course,
I
you
can
get
stand there
some.
and answer your question.
Yeah, so thank you for your very nice presentation. I am Abhishek from ISC. So since I am also working on the similar topic, so I just wanted to know that how did you manage with the in situ data that is available for 4 times a year while doing the annual analysis, annual scale assessment?
I have to use this. It's a protocol. So there's huge amount of groundwater data now available. We have this what we call India Water Resource Information System set up by the Central Water Commission, which has data for I don't know how many thousands of wells. In Maharashtra alone, I can get you the exact numbers. For each district, you will get at least 100 observation wells, which is very, very good. Any groundwater scientist would tell me. Of course, if you're dealing with the local aquifer conditions, this monitoring observation network may not be adequate, but then we are dealing with the regions, it's a very large number, and it's validated data. So that's
no, actually on annual scale, my question was like we have only 4 values. So while doing the annual scale assessment, how did you manage with that only 4 values? Because we do not have monthly values for like groundwater level.
Your monsoon, the recharge happens, 95% of the recharge in most regions happen during the monsoon.
So you have taken on only the monsoon value for a particular
We are dealing
year.
with the water level fluctuation during monsoon.
Okay. Thank you.
Yeah.
Thank you.
Okay, I think it is clear that we need higher resolved data, because it's a question of water content in the soil, and hydraulic conductivity is a function of water content, and so on. But I think he made it clear. There was a hand rise from the lady first, and then to here. Sorry. 1 minute, please. A short question, and then so that we can ask 2 short questions and 2 short answers.
Thank you for the nice presentation. I come from Maharashtra, so it was interesting for me. My question is that in the regression that you have, there is, I don't see a factor for consecutive drought years or impact of how the rainfall was, say, 2 years ago.
Yes.
And I can understand it's a shallow aquifer, but especially in the semi-arid regions where the rainfall is low, do you think there could be an impact of on the post-monsoon level because of consecutive bad year rainfalls?
That's exactly what I'm saying. The previous year's monsoon, the rainfall
No, I meant
conditions.
2 years or 3 years.
Basically, what happens is when the monsoon during the previous 2 years was bad, then the water level, depth to water level before the monsoon will be very large. So that's what is an influencing factor along with the rainfall.
Right. Okay.
Yes, that's
the
very important.
diversity, do you
Yes,
see-
that's what is captured here.
And because you capture sort of an average, is
please.
the diversity within the
So we
region
did it
also
for district, and we also did it for the state. We first did it for the state and the district, and again went back to the capturing complex conditions.
Okay, I'm sure you are available for further discussion later, right? Okay. Now, last question, please, very short.
Thank you, sir, for a very comprehensive presentation. So as you tell that Maharashtra is using lots of shallow aquifer groundwater, so are there any physical evidence of land subsidence seen due to over-extraction of groundwater? And beside the rainfall recharge, what are the other like recharge techniques you have added up to protect the groundwater resource of Maharashtra? Thank you.
Well, I am a very strong critic of groundwater recharge. Unfortunately, I wrote a paper in 2008 challenging this whole program of aquifer recharge with a paper titled Chasing a Mirage. It was published in a very popular magazine, economic. So you can read the article, why it is a failure. Technically, it's a very good idea. I'm a groundwater scientist, by the way. I started my career as a groundwater modeler, doing all the sophisticated FEM-based modeling. And now I'm into statistical modeling, symbol. Yeah, I'm old. So, I understand this. So, but the problem is, where does the groundwater deplete? Groundwater deplete in areas where you have limited surface water. Farmers first go for surface water and then they go for groundwater. So all the groundwater depletion areas in the world, not only in India, are surface water short areas. So you don't have much surplus water which can be used for recharge. That's the problem. We'll discuss it.
Thank you. Thank you.
so much.
If we give a hand to Mr. Oh, this is okay. You did it very clever. You was 2 minutes earlier, and now we had 4 minutes discussion. You see? So it works. Okay. Now I ask the next speaker to the floor. It's Mr. Tariqul Islam from Bangladesh, and he will give us a presentation about managed aquifer recharge techniques in Bangladesh. Please, the floor is yours, and please take care for the time.
Very good morning. This is Tariqul from Bangladesh, and I have been working with NGO Forum for Public Health, and today I am presenting managed aquifer research technique, an applied solution for artificial storage of groundwater to improve groundwater condition in drought-prone areas. So before going to the detailed presentation, I just brief my organization. So NGO Forum for Public Health is a national-based organization, and we have been working to promote water sanitation, hygiene, groundwater sustainability, environment management, disaster risk reduction, and climate resilience action. So Bangladesh, it's basically 5 geophysical areas: coastal areas, which is highly saline-prone area, hilly areas, and chor areas, wetland, and drought-prone area. This is basically consisting the low groundwater level areas. So here is the left side in the demarcation. It is the high drought-prone areas in Bangladesh. So the study area was identified based on the climatic condition and drought situation. So the study area is northern part of the Bangladesh called Chapai-Nawabganj district. This is the division under Rajshahi division. So Bangladesh basically three tropical monsoon, three seasonal variation on winter, rainy season, and summer season. So average rainfall in Bangladesh almost 1,525 millimeter, whereas the national average rainfall is 550 millimeter. So the study area's rainfall is less mass in terms of average rainfall. So hydrogeologically, the study area is a high drought-prone area, and this is and also the resource potentiality is less area due to the geological condition. So we have collected the secondary data and observed the groundwater level in the study area. First one is our study area. Groundwater deflation day by day increasing. Second one is the adjacent area of which is also the similar pattern. Third one is also similar adjacent sub-district of study area, which is almost similar pattern to groundwater deflation day by day. Trend of groundwater in the study area, we have seen the earlier slide. It is generally decreasing both rainy season and almost around the year. So because there is less scope to groundwater research by naturally. So rate of the change, basically we have tried to analysis to variation dry season and rainy season based on the secondary data. So almost average groundwater deflation is 0.8 to 4 meter per year, and rainy season also little bit lower, 0.8 to 0.4 meter per year. So I skip this slide. So considering the climatic condition and groundwater deflation, we identified the area and assess the potentiality of groundwater research through managed aquifer research technique, and also the quality assessment, which we after implementation of the groundwater research technique. So this is an project, and this project was funded by Swiss Development Cooperation, and we NGO Forum and Department of Geology Mining has been implementing jointly this project in the Bahrain track area. So data and method, basically we have collected two types of information, both in secondary information and primary information. So based on the secondary information, we have shared earlier few slides, and primary information we have collected we have conducted the vertical electrical sounding to assess the groundwater situation, aquifer situation, as well as the lithological situation. So we have conducted the vertical electrical sounding to identify the potential aquifer which is suitable for the groundwater research. So this is the geoelectric section from vertical electrical sounding. We have seen the from this section, basically we found three zones. One is topmost layer. This is basically consisting the clay thickness up to 22 meter. Then aquifer zone, which is zone 2. It's fine and medium sand consisting which depth is 22 meter to 33 meter, and third zone is aquator, so there is no scope to research artificial research. So this is the 3D section, 3D view of the zone 1. Earlier we have said this is the second zone. So earlier I tried to tell the major objectives of this study. So now we are going to the technical options or technical what we are doing in that area. So managed aquifer research technique is an engineering system. So which through this technique, water banking process, water research artificially using the rainwater. So this is the symmetric diagram of MAR technique which we have implemented. There are different components. One is rain gauge station, rain gauge station. Another is a roof casement of for water harvesting, and filtration unit, injection well. We have seen the symmetric diagram. Water comes to the rooftop and through the girder, and is first come to the filtration unit. After completing the filtration, the water goes to the aquifer zone. So this is the major features we have, which we have installed that area. I am not in details. So this is the rain gauge system. Second one is rooftop casement, which we have selected for catch up the rainwater. Girder, and we have installed a monitoring oil adjacent to the research chamber. This is the research chamber, and injection oil. So we are trying to comparison between the two results after installation of MAR and before installation of MAR. So we have seen the before mark, the water level gradually declining, and after installation of MAR, we have seen it's gradually increasing the water level. So we have assessed the water quality both in for pre-managed aquifer research technique and after managed aquifer research technique. So there is no any toxics both after researching or researching of managed aquifer research technique through water in the aquifer. So we have few observation, and it's obviously early recovery system to contributing the protecting declining of groundwater level. Improve your year-round availability of groundwater, because before installing the mark, especially in the dry season, the hand tubes are not fully functional. So we have found after installing the mark technique, we can easily get the water through using the hand pump. No evaporation loss due to the underground storage. Technology is so easy to installation, and no need record any skilled manpower. Underground storage space is required. Roof casement is required available. I just skip this. And finally, I say this is less operation maintenance as well. We have found the major issues in the community level. So the community level is less participation, because community are getting benefit indirectly as well. So that's why community participation is less. Finally, I said this model already has been replicated by other agencies like BMDA, Bahrain Multipurpose Development Authority, and Swiss Development Cooperation Authority. So this is my last slide. So thank you from my side.
Thank you, Mr. Islam. So is there one short question now? Yeah, there is one short question. Just please use the microphone, because we are also streaming.
What's the rainfall in this area where you are doing this experiment, and what is the cost of harvesting this water from the roof catchment using all the systems?
We used the community catchment, so there is no additional cost for the catchment area. System is less cost, like $200 US.
Yeah, Thank you. I see some skeptical faces, but that means there is still demand for discussion later. Thank you. So, thank you very much. I give you a hand to you. And I ask the next speaker, Mr. Paul Pavelic from the International Water Management Institute in Australia. And he brought us a presentation with the topic Establishing Entry Points for Sustainable and Inclusive Groundwater for Use for Agriculture in the Mekong River area. So, Mekong Basin, the floor is yours, Mr.
Thank you, Dr. Jürgen. Good morning, everybody. I'm Paul Pavlik from IMI. IMI does not have an office in Australia. I'm based there, but I'm affiliated with the office in Lao PDR, if you're curious to know. And I'm not talking about managed aquifer recharge, although I probably should be. We'll be talking about agricultural groundwater use in a couple of lower Mekong countries where data is very scarce. So the type of information we're collecting is very much socioeconomically oriented and probably fairly basic, but appropriate for the particular situation in terms of groundwater governance of these particular countries. This is a project that has been running for the last 2 years, supported by the Summernet program, operating out of Bangkok. And our partners are the National University of Laos and the Institute of Technology of Cambodia, because we're working in Laos and Cambodia, as you'll realise in a moment. And my co-authors, I'd like to give a quick acknowledgement to who you see there, virtually the entire project team. Now, we're focusing on groundwater use for irrigation, and this is some work that IMI had done some years ago, mapping the extent of irrigation, including with groundwater across the greater Mekong sub-region. And the point I want to make clear to you is that use identified by remote sensing, the amount of use by groundwater is very limited, less than 1% of the cultivated area, particularly in Laos and Cambodia here, very low, perhaps a little bit higher in Thailand and Myanmar, but certainly very low. So we picked up 2 countries where groundwater usage for agriculture is very low and wanted to understand what is the situation there and how can we overcome the constraints. Now, one of the reasons why we want to utilise groundwater for irrigation is not only to increase the area under irrigation, increase food production, diversification, but also to adapt to climate change, as Dr. Mukherjee had mentioned this morning. And of course, when we think about this, we want to do this in a way that's sustainable, that doesn't induce groundwater depletion, and is inclusive of all societal groups. So our objective is really to have a good look at what's happening in terms of groundwater use and identify entry points for sustainable and inclusive expansion in these two countries. So we chose a couple of focal areas. Broad areas here are southern Laos, Champasak province. It's an area called the Bolavan Plateau, which is another basaltic region in the Mekong, volcanic terrain, highly productive, and where they generally grow rain-fed coffee or cassava. But there's emerging signs of use of groundwater for various cash crops. And as a complete contrast, we're working in southeast Cambodia, in Prey Veng province, where it's the floodplain of the Mekong River, and there it's paddy rice virtually year-round. Short duration varieties, mostly irrigated with groundwater. So 2 very contrasting scenarios. Little bit of a zoom in our study area. This is the 3 villages that we selected in both Laos and Cambodia. In Laos, the villages are quite contrasting in terms of the levels of poverty, in terms of the degree of ethnic communities that are present. Whereas in Cambodia, it's much more homogeneous in terms of ethnic groups and sort of socioeconomic status. And we did household surveys in those countries, 50 in each country, 100 in total, and we supplemented that household level survey information with stakeholder engagement at the community level, at the subnational level, and also with information from the literature to try to drill a little bit deeper. So our findings in southern Laos that the majority of households use groundwater for domestic purposes. In the poorer communities, there's a lot of sharing of water, either through neighbouring wells or through community wells, and that the majority use 60% or so use groundwater for low-intensity agriculture, mainly home gardening, and in some cases for commercial agriculture, but it's very, very limited. There's also use for livestock, and most of these households use electric pumps, but there are issues in terms of the reliability of the electric supply, which makes it difficult for them to utilise groundwater for their livelihoods when they don't really know if they'll be able to turn their pumps on. In the Cambodian situation, there is no community wells. The groundwater is much more accessible. It's much shallower than the uplands of Laos, and they all have private wells. And about half of them, a little under half, use groundwater for growing paddy rice year-round, and there's a lot of use for livestock as well. These pumps are high capacity, 10, 20, 30 horsepower pumps, pushing out a lot of water, and they need that water to irrigate rice, which is very water consuming. And what we've noticed now with the rise in fuel prices, that many of these farmers who had gone from canals to groundwater are contemplating shifting back to canals because of the reduced lift required, the lower energy situation associated with canals, which was quite intriguing for us. If we look at the groundwater storage trends in the Laos situation, we'd done some technical studies ourselves in this area, and we're able to map out the well infrastructure and depth of groundwater, and it's around about here, 7 or 8 metres below, 8 or 9 metres below ground surface, quite deep, but we don't have time series data to know what the trends are, but all the indications from the community and the local officials are that there isn't a situation of overuse yet. It's still quite low relative to replenishment. Whereas in the Cambodian situation, where we have a lot of groundwater information in this area dating back for several decades, you can see the trends from 2000 to 2010 and 20 is deepening of the groundwater level, certainly signs of groundwater depletion in this area which are evident, and I could show you much more detailed data than I'm presenting here in this slide today, if needed. We also asked the households what are the key constraints to expanded use of groundwater for agriculture. We got a mixed response of answers, but in terms of Laos, the main constraints to them is working capital to buy fertilisers, to buy pesticides, to things of that sort of nature. Family labour was also a constraint because there's a lot of push for rural communities to go into the towns and cities to work for higher salaries. In Cambodia, it's mainly fuel prices and inadequate markets to support diversification opportunities that may be present. And in both cases, the households would like to utilise more land for agriculture, but are constrained in that way. So just in conclusion, there is dependence of groundwater in both of these countries, particularly in Cambodia. We asked the communities about climate change as well, and in the Laos situation, they weren't aware of climate change impacts, which is surprising to us, even though the scientific evidence clearly shows increased temperatures, but certainly there's no direct evidence, not in terms of floods and droughts and things of that nature, whereas in Cambodia it's quite apparent. There is much more flooding now than there used to, but also there's been a lot of damming within the Mekong region, so the whole hydrologic system has altered in that part of the Mekong system. So we have to consider climate change alongside the development of the river for hydropower. So high fuel prices and restricted access. And in terms of Laos, they really know very little in terms of the opportunities for accessing groundwater. So it's a lack of knowledge, a lack of capital, and lack of capacity there. And interestingly, we didn't see water as one of the top 3 constraints. It comes out at number 4 or number 5 on the list, even though you saw that depletion trends are there. It's not at the top of their list. It's something that's much further down the track in terms of household priorities. So what we see as potential recommendations is opportunities for solar-powered pumping to overcome uncertainty in terms of electrical supplies in Laos, to overcome high fuel prices in diesel fuel prices in Cambodia, and opportunities to diversify beyond major crops. And we didn't see much in terms of the farmer cooperatives operating there, and perhaps some collectivisation of action amongst poor farmers could be useful to provide credit and access to knowledge to enable these types of practices to become more mainstream. So thank you very much. Kaprong Kap.
Thank you very much, Mr. Pavelik, also for keeping time. I would allow a question to Mr. Pavelik. Is there any question in the... Yeah? Mr. Dinesh Kumar.
Paul, it was a very fascinating presentation, very, very important findings. I was wondering whether you have any data on this water balance of the regions. You're talking about the groundwater depletion in these two areas, and I understand they're high rainfall areas. So, and then all this paddy which is being irrigated, most of the water goes back to the system. So the real consumptive use of water for paddy is a small fraction of the total water you're applying. So still you see depletion there. You have very high rainfall, very high recharge, and then you still see depletion. So you do have any water balance estimates for the region? It's a very, but the most important finding which I found is land availability is becoming a very big constraint for some of these high rainfall regions. A point which I have been making for Eastern India.
Yeah.
It's not a groundwater irrigation, but it's a land availability which is becoming a big constraint. It's not access to groundwater, but the access to land, which is becoming a big constraint for farmers from enhancing their, generating more surplus from agriculture production. Thank you.
Mm-hmm. Yeah, thank you, Dinesh. In this study, we didn't assess the water balance, but in parallel studies, we are, particularly in the Cambodian situation, where we're doing technical assessments of the water balance, including developing a groundwater model to really understand the water balance components. It's still a work in progress, but we're aiming in that direction. Thank you.
Okay. Thank you. Very short? Very, very short.
Yeah. Thank you, Paul. My question is very good results, a lot of insights about the two communities. Do you have any information whether this is a general tendency over larger regions, larger areas in that region about groundwater use, or it varies a lot spatially?
The Mekong, as you can imagine, is a very heterogeneous region. We picked a couple of typical areas in these data-scarce regions of Laos and Cambodia, so-called least developed country situations. But we know parts of the Mekong Delta are intensively used for groundwater. We've studied the groundwater irrigation in the Chao Phraya, the upper and the middle there, and there they grow sugarcane and rice year-round, and there are also evidence of a groundwater depletion. So the types of signatures we're seeing in Cambodia are also being seen in Thailand, for example. So there is a bit of commonality across the region, showing that we need to, if we're going to utilise groundwater intensively for agriculture, it's better to get the management right rather than have problems and then try to retrofit thereafter. So in cases like Laos and Cambodia in general, try to get the management systems of management right before we have emerging exploitation. Thanks.
Thank you, Mr. Pavelich, for also answering these questions. And let's give hands to Mr. Pavelich. And yeah, there will be some minutes time after the last presentation for discussion, so save your questions. And I would like to welcome Mr. Abhishek. He's from Tokyo Institute of Technology in Japan, but talking about a drastic depletion of groundwater in India. So, Mr. Abhishek, please come up, and the floor is yours. We are very excited for your presentation.
Yeah. Thank you. Yeah. So I am Abhishek from IISc India. But I will present here the work that I have done at the Tokyo Institute of Technology, Japan. So I will talk about the drastic depletion of groundwater in India, and there is analysis on a statewide analysis that nationwide, not on the basin scale. So building upon the previous discussion that we are having in this conference about the importance of groundwater, I will just briefly talk about the groundwater importance in several sectors. So as we know that about only 1% of the global liquid fresh water is accessible to humans. And although this number looks very small, but even a small change in this number may put around half of the world's population as the state of water bankruptcy, and may even lead to the regime changes of some basins, say for example from humid to arid, and that may never come back to their original state. Also, groundwater plays critical role in several other sectors like modulating hydroclimate extremes and freshwater availability, food production. Just to say an example that we have seen, about 90% of the groundwater in India is used for irrigation, and that ultimately goes to the crop production. But the like confounding impacts of climate change and human activities, about reservoir impoundments and groundwater extraction, among others, have like altered the water cycle and also changed the water storage conditions. And in water storage, the groundwater is, in India, groundwater is the major part. So there has been like increasing evidence about the unsustainable groundwater depletion in India, but most of the studies are either on the basin scale, or they are just focused on some regional scale, that is northwest India, some 2 to 3 states. So here we have used, we have studied the pan-India groundwater dynamics for the past 2 decades using several data sets. And here, since the basin scale studies may be helpful for understanding the hydrological cycle and various earth system processes, but they might conceal the inferences from a policy making perspective in India, where we have seen like interstate water contestations lasting even for more than 2 decades in some cases. So here the like in situ data traditionally is believed to be the gold standard, that is the best data for validation. But in India we have a dense network of groundwater wells, but that is observation is available only for 4 times a year, that is in January, in May, August and November. So and other advanced methods are also available, like global hydrological model. Many of experts I can see, like in global hydrological modeling, they are there. And then we have GRACE data, and then we have data-driven methods. So all these methods have their own advantage, but they suffer one or more of the shortcomings in terms of maintenance, or maybe spatiotemporal extent, or the uncertainty and propagation errors. So therefore, in this study, we have utilized a optimal strategy using multi-source data. That is, we have used the data from all these sources. So first, we have used the GRACE data as terrestrial water storage, that is total water stored in the land mass. Then using water balance equation, we have estimated groundwater as the residual, while using the surface water, soil moisture from global hydrological model. And then lastly, we compared the groundwater storage dynamics with the in situ data. So this is the schematic of the study. So we I will just focus on the most interesting part, that we have used the groundwater data from the observation wells. Those are around 54,000 observation wells pan India, and use the 3 machine learning methods to fill the data gaps. And then we have used the water balance equation to study the spatiotemporal dynamics of groundwater. So these are the results. So this is the groundwater level time series at a monthly scale for all of the states of India. So we can see that all 3 machine learning methods successfully filled the data gaps in the in situ data. And but we can see some performance disparities in some states, say for example Rajasthan, where we have long-term declining trends due to water extraction, primarily due to water extraction. But in all other states, all 3 methods generally perform well. So the shaded gray area is the time duration where we have monthly data available from state agencies. So during this monthly data available duration also, all three methods are performing well, we can say. And after this one, so we studied various water storage components and precipitation, evaporation, and examined how these things are varying. So here we can see that groundwater is the major component for TWS throughout the India, and the declining trends in northwest India, mainly comprising of 3 states, Haryana, Punjab, Rajasthan. So although this is we know there have been many studies that groundwater is decreasing, but what we found is that the decrease is more acute than the previously thought or estimated, and that is also confirmed by the in-situ data, dense network of in-situ data. And the soil moisture, the positive soil moisture generally supports the notion of that there is increasing irrigation. And so if we estimate this groundwater loss, so it comes about 200 cubic kilometer. And if we calculate this as compare with the water storage capacity, so it comes out to be equal to the biggest dam in terms of water storage in Zimbabwe, and about 64% of the sea level rise that would have been caused due to the glacier melt during the past 2 decades. So, but assuming that there is whatever groundwater is there, that is, there are no other losses. So there is urgent need for revised policy making. So this was in conclusion, we have studied emerging trends of groundwater variability and groundwater level, and we have seen the state level assessment for better incentivizing the water resources allocation and policy making. And groundwater is the major component. So what we infer is as previously have been discussed in some of the sessions, we should to maintain a sustainable groundwater for future generations, we should focus on the demand side rather than the supply side, because if we increase supply, then it will have some subsequential effects on water quality, land subsidence, or seawater intrusion, mainly in coastal areas. So we need to think about the demand side, maybe incentivizing or subsidizing the drip irrigation, among others. So results will enable a robust mitigation for various impacts of reduced water availability and efficient and effective water resources allocation in India, and with broad methodological implications for other regions. We are facing similar water crises, maybe Iran or Central California Valley in USA, among others. So thank you for your attention.
Thank you very much, Mr. Abhishek, for your presentation. Is there now a direct question? Yes, there is. Okay. First direct question to Mr. Abhishek.
Yes, thanks for your presentation. I was wondering about this shifting from basin scale to state scale, and I understand in terms of policy making why it makes sense. However, I was wondering, wouldn't it make sense to make policies rather on basin scale than on state scale? What's your reflection on that?
Basin scales are of course better for understanding how water moves through the aquifer and various earth system processes, but in India we have this thing we can understand by example of transboundary river basins, but a little bit in exaggerated way. So transboundary basins span through various countries. So similarly in India we have river basins spanning through various states, and we are a democratic country. So although we can have a central legislation, but when it comes to the implementation, so there are several factors, as we have discussed in several keynote speeches in this conference. So that's why we have to have a better understanding, not only on the basin scale, but on the state scale also, to enact some feasible legislations on ground to reduce the conflicts, interstate water conflicts, and to better manage, especially at the state levels. Yeah, please.
Hi, Abhishek, very useful presentation. Abhishek, I think the question about this basin, I think is very important. I think we are confusing, unnecessary confusion is created. See, the basin scale matters when it comes to surface water more, because aquifer boundaries are anyway not going to are not coinciding with the river basin, the surface, the hydrological boundaries. So, it's anyway, and further the assessments of groundwater is already done even at the district level, even sometimes the lower administrative units, in the blocks and all that. That's the reason, because the aquifer boundaries, we don't even know actually the real boundaries for the aquifers. The point about this you have mentioned this 200 cubic kilometers, billion cubic meters of water lost from northern India.
Yeah, so it is
serious. I think that number is wrong. See, the total groundwater abstraction, as per the official estimates, of course you can contest it, is about 240 billion cubic meters in the whole country.
230, yeah, I know.
230 to 40, you can contest it. But the groundwater loss, what do you mean by groundwater loss?
So this is the volumetric groundwater lost from the 2 decades.
In two decades.
If we assume that
2 decades.
Yeah.
Okay.
In the past 2 decades.
Okay.
Yeah. Not on annual scale.
That comes to 10 billion cubic meters. Even that's a very big number.
Yes.
Please check it.
Yes,
even 10 billion
is
cubic meters is a very big number.
Yeah.
And because the depletion corresponding to that loss will be huge, enormous.
Yeah, so that is including these 3 states and also the UP and the adjacent Bihar and also.
There is a small pocket where the groundwater is depleting. Rest of its groundwater depletion is a phenomena in Punjab, parts of Rajasthan,
and Haryana,
Gujarat, and not even Haryana, and some pockets in southern India.
Yeah.
You know, this is being what you call sensationalized. It's a serious problem in those areas, but it's being over sensationalized, romanticized. It's a problem, but it needs to be tackled. It's not so big a problem, not whole country. But there are many areas where groundwater levels are actually rising.
Yeah, but those rise may be some localized. So yeah, we may need to see that further. Yeah, thank you for your comment.
Yeah, thank you very much. Mr. Dinesh Kumar, I would like to answer the question a little bit different than you answered it. Of course, we have basin-wide thinking for rivers, but we also know basins, of course, for the groundwater. It must not be the same. It's different. It's more difficult to estimate this or to determine this, but it is also, we can define a basin thinking. Groundwater don't know any administrational borders, is not interested in this, and so this is a very important step in thinking of or looking and administrating water from the perspective of water and water cycle, let me say. So very interesting discussions. We have 4 minutes left, and now the floor is open for all the presenters. Do you have any questions to the presenters? If you allow, I would ask you to come in front, so that you are visible and that auditorium can give the answers, questions to you and you the answers. Please. Yeah, there's one in the back.
My question is to Dinesh. My name is Ravi from India. So I just want to know the process for the districts that are dominated with irrigation and the districts that are dominated with industries on the groundwater fluctuation, in particularly relevant to Maharashtra. So can you please comment the role of the irrigation in the districts that are dominated with irrigation and districts that are dominated with industries? You know?
Actually, I had not done that kind of a segregated analysis, but I can tell you where there are industries, there is localized phenomenon of groundwater depletion, what we call drawdowns, cone of depressions, where there are big industries and there are big cities, and where cities are dependent on groundwater. Now, I can cite one example of Ahmedabad in Gujarat. There is excessive drawdown. Because of excessive drawdown, there is cone of depression created. But the agriculture continues to be the largest user of groundwater in our country. Not only the country at the national level, but even in states. Agriculture is still the largest user of water. Many industries are actually not using so much groundwater because they need better quality, high quality water, and they are purchasing water from the state, from reservoirs. So water from the reservoirs is being allocated for industry, and they are paying for it. And in fact, many state water departments, their main source of revenue is the water which is sold to the industries, and not from agriculture, not for irrigation.
Thank you.
Another question. The lady, maybe the lady was half a second faster. Next time.
Yes, I was wondering, so since we're in a water security and climate change conference, and well, I came a bit late to the session, unfortunately, but the presentations I've seen were mostly about how humans influence, or human activities influence groundwater level. And I'm really not a groundwater expert, so I was wondering what are the effects of climate change on groundwater? Could you reflect on it, or like what is the current scientific state, since I was missing that kind of perspective a bit in the presentations that I saw?
Okay, thank you a lot. Your question is now not answered, because this is a question we have to all of you, and every one of you have to give one sentence answering this question. Thank you. This was my question, you know, at the end. So, yeah, there's one. But prepare for answering this question. How is your presentation related to the topic of the conference? That is what we ask everybody. So, yeah, your question.
Thank you, moderator. Abhishek, nice presentation. You know what is happening in India that we see, I mean, there is a lot of this contradiction when it comes to, you know, how the groundwater level is varying. You know, somewhere you will find people come and, you know, depending on the time period they are considering for, you know, kind of an assessment, they will say that it is going up, somewhere it is going down. I think capturing the seasonality here is very important. Like, which is that season when you see that the groundwater trend is decreasing or increasing. So, and I know that there is a lot of good observed data set available. I mean, I think CGWB alone is having some 15,000 plus observation wells across country, and they are, as you mentioned, they are measuring this water level 4 times a year. So have you also performed that seasonal level analysis? Because it is very crucial when we talk about the variability that we experience across India, spatial, temporal. So it is very important to capture that seasonality and then probably see how actually that variation or increase, or let's say the change in groundwater level is happening. And what was the time period that you considered?
Yeah, thank you for your question. So I will answer in several parts. So first one is the seasonality. So we have done the seasonality analysis, but in interest of time, I did not show that. So regarding seasonality, our results coincide with what Professor Dinesh has said. Like the aquifers in the peninsular India, so Maharashtra and all other states, so they have high seasonality because they are having hard rock underlying aquifer. So for alluvium aquifers, so seasonality is not that much high. Regarding the second part, so we have used the in-situ data from all of the groundwater wells, and we interestingly we did not remove the wells which were dry or defunct, because the main reason was that for the hard rock aquifers, some well may go dry in a season, but that after a precipitation that well may again have readings for water level. So we have not excluded that one. So that might be one of the reasons that we observed like higher than previously perceived groundwater loss from the region. And third part I forgot. What did you ask? So I forgot what was the one small part, third one. So maybe we can discuss. Yeah, thank you.
Okay, thank you. And yeah, there is one more question. I'm very happy that we have.
Thank you. I'm Wendell. I'm from the Asian Institute of Technology. My question is to Shubham. I'm interested in your modeling. During your modeling, have you ever found any the appropriate storage time frame after injection, and have you ever and what is the salinity value during that time and after extraction? Thank you.
We have different study areas. So one of the study area which is having around 8,000 microsiemens per centimeter electrical conductivity in that area, the salinity level, and 2 areas are having around 5,000 microsiemens per centimeter. So we are having storage durations, as I understand, as per your question, that regarding the storage durations. So the storage duration in the areas which are having less groundwater salinity is a longer period in comparison to the areas which are having higher groundwater salinity. So we have variated also the storage durations, that what according to our needs, that how much water we want to take out, and as per that we have fixed that this much storage duration we can work it out. Other than after this we cannot take more than this water. So this is how we have taken from the model.
So thank you very much. Look at the presenters so that you can find them in the coffee break, yeah, and ask more questions. But now, due to time, the question from the lady, exactly how is your topic linked to the topic of the conference? One sentence now from each of you.
Yeah. Look, it's an important question, and in this area, a plethora of work has been done in this area, but not in the lower Mekong. It's very limited, and it's sort of a next generational sort of question that we need to answer. We still have to build the building blocks in terms of understanding the hydrogeological systems and where development can take place. And then we'll be able to do the types of analysis. But we know climate change is affecting both the supply side to groundwater, the recharge rates, but in the Mekong we really don't have a good handle on what the baseline recharge rates are anyway, and the demand for water as well, but we haven't really done the analysis yet.
So yeah, in the era of combating with climate change, we are having shortage on the surface freshwater supplies, and as we know that groundwater salinity is also increasing. So I think my studies on aquifer storage and recovery, it will be helpful while combating the climate change by the storage within saline aquifers.
I think it's a very brilliant question, which is not yet fully answered. In our presentation, what we did is not looking at the climate change, but the climate variability effects of climate variability on groundwater recharge, fluctuations and recharge. So what we found is that high rainfall areas, the water level fluctuation, which is an indication of the recharge, is much higher. But then the variation is not linear. How it varies, it depends on the geohydrological environment. Before the recharge, before the monsoon rainfall starts, what was the groundwater condition? That also influences and then how much groundwater space is available in the aquifer. That's a very, very important factor. Now you can extrapolate this. Now what we found in India, looking at many, many regions, many, many river basins across the country, many basins, there is an increase in rainfall over the last 100 years. Because we have data for 120, 130 years for many locations. So some regions, the rainfall has increased. In some regions, in some locations, the rainfall has declined. So if you look at region as a whole, you don't find a much big change. So if the rainfall is increased, it will have definitely some effect on the amount of recharge, because we get recharge only mainly from during the monsoon season. Thank
you. Yeah. It's obviously contribute to climate change, because due to climate change the drought vulnerability has been increasing. So groundwater research also contribute to the preserve the aquifer water table. Also it's obviously contribute to the vulnerable communities, I think.
Yeah, so in my viewpoint, climate change cannot be seen as a separate aspect other than the human interventions. Just to say one line and example, if we have less precipitation, so surface water is not available, so we tend to extract more groundwater, and that's what we have seen in my presentation or in our work. Thank you.
Thank you. So it's now difficult for me to add some more. What I learned is that we talked about the management of an invisible resource. Let me say invisible in apostrophes. It's underground, invisible, but it's also incredibly valuable. So groundwater is a very valuable resource. It's in most cases it's very old. In most cases it is clean. It's a clean resource. And of course, due affected by climate change, we will have all these stories with aquifer storage and recharge, and I hope that all, or maybe the linking of water extremes, floods and droughts, yeah, maybe we can match it and can more recharge, but then we have all these aspects with groundwater quality, which is a huge, huge topic. Yeah. Today we talked about quantity, but we have also then to talk about quality. So I would like to thank you, the presenters. We had, unfortunately, too less time, right? You agree? Okay, I agree also. Yes. No, we need more, but we had only less. You found more time, okay. And I thank the presenters. I thank the auditorium for wonderful questions and for supporting the discussions. So my hands now for these people and for you. Thank you. Up end.